Okay, so hi, I'm Jade, and before I start, I just want to say that my grandma, who's super into planets, has been watching a lot of our CCTP talks this week, even though she doesn't actually speak English, so she's watching right now, so coucou, that means hi in French, okay. So here we go. So I'll be talking to you about developing an empirical test for the concept of the habitable zone, more precisely about testing for the silicate-weathering feedback. So in the near future, new and powerful instruments are going to present us with a great opportunity to characterize promising, potentially habitable or inhabited planets in a lot more detail than we presently can. So in this spirit, so far, the planetary science community has been focused on a system science approach when thinking of exoplanets. Now, what I mean by system science is represented by this big, thick arrow here, where we'd essentially be spending a lot of time and resources to try to characterize a very small number of objects in a great amount of detail. So a great example of that would be the Juno mission. However, when we leave the solar system and we start thinking of exoplanets, there's some new challenges and difficulties that we have to consider. First, we already expect terrestrial planets to be very diverse in the structure and compositions of their cores and atmospheres. So this will make it very difficult for us to formulate a testable hypothesis, because we just don't know what to expect when we're going to be looking at one or two planets. We're kind of going into blindly. Then, of course, the instruments themselves are going to have inherent practical limitations, as has been discussed extensively today, and that could make us miss important biosignatures. So to illustrate this here, you've got the spectrum of Earth's atmosphere, and of course we have some strong signatures here that would be amazing to see on an exoplanet. But unfortunately, an instrument like HABEX and LUVOIR won't be able to see any of the blue shaded region. Will be limited to about 1.8 micron, if I'm correct. So that region has here much weaker signatures that would still be great to be able to observe, but since they're weaker, we might miss them from the instrument not having a sufficient signal-to-noise ratio, or if there's clouds and things like that. And another addition to this is that even if we're able to characterize one or two molecules for a given planet, by now we've already come up with enough false positives and false negatives that this is going to be really difficult for us to interpret any list of biosignatures. Okay, so because of all those kind of difficulties, a system science approach might lead us to end up empty-handed, so with no conclusive evidence of habitability, and especially not of a planet being inhabited. So to maximize the scientific return of future missions such as HABEX or LUVOIR, we might need to start thinking of complementary approaches. And the one I'm talking to you about today is a statistical comparative planetology approach, which might allow us to more robustly test for some scientific hypotheses. So with this kind of statistical method here, as illustrated by this cartoon, we'd be spending much less time and resources on each individual object, but we'd be applying each type of measurement widely, so here on a large sample of planet. So that would be really maximizing what we can learn from each type of measurement. So a great recent example of this kind of statistical method is by Leslie Rogers, who used very, very low precision, as you can see, huge error bars, mass radius measurements of a lot of exoplanets to infer the radius at which planets become rocky. So she found that it was at about here 1.6 Earth radius. And if Leslie had instead taken 2 or 3 of those points and tried to make them more precise by doing further observations, she would have never been able to make such an important scientific statement. Okay, now what I want to do with this kind of statistical method is to test for the concept of the habitable zone. So the canonical habitable zone, its concept, predictions, and assumptions have not been tested observationally, but we always assume that they're true. So an important assumption of it is that the silicate-weathering feedback functions on habitable planets. But does it? We don't know. So that's a really important mechanism for us to understand, as the entire concept of the habitable zone relies on it to regulate surface temperatures by cycling CO2 in and out of the crust of the planet. Now, if we assume that the feedback does functions on exoplanet and we observe 5 of them here, so terrestrial planets of a decent enough size, so here that's what we should be able to observe. So here on the y-axis, you've got the mixing ratio of CO2 on a log scale, and on the x-axis, the irradiation in units of Earth insolation, sorry. So if we take one planet here, that's much further away from its star, so with a lower value of irradiation, you need a much higher amount of CO2 to maintain habitable surface condition. But if we take this planet here, which is much closer to its star, you'd need a lesser amount of CO2 to maintain similar conditions. Now, of course, we might end up with large error bars because of uncertainties such as surface temperature, surface pressure, greenhouse gases, and especially clouds, and instrumental uncertainty. But what we want to do to be able to detect the silicate weathering feedback in future observations, we'd have to be able to resolve this downward trend here from a zero slope, which would mean that the feedback is not functioning. So for that, we'll need to be able to marginalize over our error bars here, so over all of our planetary uncertainties. So in order to be able to successfully discern this downward trend here from a null slope, we're going to need to observe a decent amount of exoplanets, because as you can see here, if we only had 3 planets, we would be able to say nothing about whether or not the feedback functions, right? But for 5 planets, we already see a downward trend. So the dream here, so my entire project, is to try and determine how many planets we're going to have to observe in order to do that. So in order to resolve this downward trend here. Okay, and the first thing in my statistical method is to get some data. So to do that, I use a radiative convective model called CLIMA and a radiative transfer model called SMART. And I keep all of the planetary parameters fixed, so 1 bar surface pressure and so forth. And I have 4 different curves here as an example for 4 different values of surface temperatures. And I compute what the CO2 needs to be at a given value of irradiation in order to maintain that surface temperature, assuming the feedback functions, right? And so let's just check that this checks out. So if we go from lower to higher surface temperature here at a fixed value of irradiation, we need a higher amount of CO2 to maintain a higher surface temperature. So that's good. But you also should notice from this plot that surface temperature is an important uncertainty parameter, as we've got a pretty wide spread in the different curves that we can get. Now, another example here is for methane. So if we keep everything about the planet constant, but we add a given amount of methane, and right away what should strike you is that it's a much less important uncertainty parameter. As for modern Earth, here the blue curve, and Archean Earth, the red curve, we don't really have that much of a spread in our curve here. Okay, so now we have our data, but then to actually do our statistical method and determine how many planets we need to resolve the downward trend, we're going to need some tools. So first, we're going to use probability distributions for each uncertainty parameter. So as an example here, it is for surface temperature. And you might think that since a planet can be anywhere in the habitable zone, it should be able to have a uniform distribution from 273 to 373. But in fact, previous work has showed that if a planet has a functioning silicate weathering feedback, it should maintain its surface temperature around Earth current surface temperature plus or minus 20 Kelvin. So that's why we're able to use this kind of bell curve distribution here. Okay, now I'm going to lay out my entire statistical method for you. So first, we choose a number of model exoplanets, say 3. Then, for each of those 3 planets, we draw surface temperature values from the distribution I showed you here. So that's where this this tool comes into play. And we draw effective irradiation value from a uniform distribution, because yes, the planet can be anywhere in the habitable zone. Now here, I'm only considering surface temperature as an uncertainty. But when I consider all of my parameters, such as surface pressure, clouds, and so forth, they're also going to be drawn for each planet here from their respective distributions. But let's just pretend we know all of that about the planet, except surface temperature. Okay, So now for each planet, I use my data that I previously showed you, so that's where the data comes into play, to interpolate the CO2 for each of those planets. So given a surface temperature and any radiation, how much CO2 is given by our data here. Then I add some instrumental noise to those values of CO2, and I compute the radiation CO2 slope for the given amount of model exoplanets that we have. And I repeat this entire thing 10 to the 5 times. Now, something to realize here is that a lot of those slopes are going to end up being positives because we have large error bars and uncertainties. So especially if we have only 3 points, actually a good proportion of those 10 to the 5 slopes are positive. But when we add model exoplanets, most of them end up being negative, or all of them. So here, this plot illustrates my previous point. So for a low number of planets here, 3 or 4, a good portion of the slopes end up being positive or near 0. So that's no good to detect the feedback. But when we increase that number of model exoplanets to those higher values here, most of them are negative. So of course, the more planets we can observe, the better. No surprise. Okay, so we needed a condition to decide on what number of planets is sufficient to have enough negative slopes. And for that, we use the power, which is here the fraction of slopes with p-value less than 0.05. So that gives us how many slopes are clearly negative. And we decided that this power had to be 0.8, so here, which means 80% of the slopes are clearly negative. Now, in real life, a power of 0.8 would mean that if we observe that given number of required planets, we'll have an 80% chance of detecting the feedback, given that it actually functions on exoplanets. Now, of course, observers might end up telling us that having an 80% chance after doing all of that work isn't enough. And in that case, we'll have to update our work to reflect what they actually want. But here, let's just take it as granted. For surface temperature as only uncertainty, we'd need about 8 observations. Of course, that number is going to grow as I add my other uncertainty parameters. But that plot is the dream of the project when I start including all of my parameters. Okay, so that's it for what I did so far. But my next step, as I've mentioned a couple of times, will be to include all of the uncertainty parameters for the planet. For that, I first use a Sobol sequence, which essentially gives me a sparse multi-dimensional grid of my parameters on which to do smart runs, because those, if anyone has used smarts, those take quite a while to do if you have a large parameter range. So this is a lot more efficient than using a uniform grid. I definitely recommend it. Then I'm going to need to look into a lot more of the how much instrumental noise we're actually going to get from CO2 observation with LUVOIR and HABEX. I haven't started looking into that, so if you have recommendations, that'd be great. I think I might need to talk to Kat a little more. And then I just essentially do what I've been doing so far, the same quasi-Monte Carlo method, to determine how many planets we'd need to detect the silicate-weathering feedback. Okay, so that's it. Those are my conclusions. I leave them up here. Thank you.
We've got time for a couple questions.
Very, very interesting work, Jade.
Thanks.
You're basically starting with the premise of the classical CO2 water habitable zone. So you're getting these slopes for that, but real planets will have other greenhouse gases, and so there'll be this noise from secondary greenhouse gases, like in our CO2 hydrogen habitable zone and CO2 methane habitable zone concepts that will change the behavior of your curves. Have you considered that? How would you address that?
Okay, so exactly. So that's why we need enough planets, because of all of those uncertainties. Like we're not assuming that a planet's only going to have CO2. It could have a range of other gases, like, as you said, methane, for example. So the plan is to assume that we don't know what the planets have, because we want to pick, for example, 20 planets to look at, and we're not going to know in advance what gases those planets have. And with a sufficient amount of planets, though, we should be able to marginalize over any changes that that curve will have because of those other parameters, if that makes sense. So that's why we need a sufficient amount of planets. Since if we might have CH4 and different surface temperatures, for example, looking at 5 planets just won't be enough for us to detect the feedback, right? So we probably will need in the dozens, I think. And from Chris Stark's presentation, I think for that we'd want at least an 8-meter telescope, but yeah.
Yeah, so you think you'd be able to infer these other gases or from
we
the
don't want
slopes,
to infer them. We want to make quick and cheap measurements of CO2, right?
Okay.
The only thing we want to do, so the whole point of this statistical method is to be able to characterize one gas for that planet instead of having to characterize all of them. And that's where the certain number of measurements come into play.
Okay.
Right.
All right. Thank you.
I think it's off, yeah.
Hi. So, of course, if you were ET and you were looking at our solar system, you would see a lot of CO2 on Venus and no CO2 almost, or a very thin atmosphere, I mean, on Mars. And so you might infer that this weathering feedback didn't work in our solar system. But
I knew someone would ask about
Of
Mars.
course, we're in this post-weathering phase on these planets. And so you might conclude the wrong thing about the whole hypothesis in the first place. So
Right.
what hypothesis are we actually testing?
Well, so we don't have to look at all the planets in the same system, first of all. Then I'd say that Mars is a really special case because of how small it is. And hopefully the planets that we're able to choose for such a test will already have an idea of their radius from previous measurements, say using TESS, for example, or even James Webb. So I'm hoping that we'll be able to purposefully not choose small planets just because those would make it more difficult. But we're also going to want to choose planets that are of a terrestrial size and in the habitable zone. So we're not going completely blindly and looking at the sky. Yeah.
Okay, thanks, Jade. And some of the assumptions that you made are very centered on Earth at present. For example, the temperature distribution that you assume, it may be representative of Earth today, but not of Earth's history. I think most of Earth's history was warmer than it is today. So I might encourage you to use a little more agnostic priors on what temperature and what other planetary parameters there are.
So I actually used data from Chris and Santoton, so Josh, who looked at Earth history and its surface temperature and essentially used a model and actual data to come up with this distribution. But I do think that distribution would need to be broader than what I've done so far, but we can talk later about the paper you're mentioning. That'd be great.
Okay.